We are very happy today to have Junhwi Lim, who is a PhD student in mathematics at Vanderbilt University, where he has been studying under the supervision of Professor Dietmar Bisch since 2021. His research focuses on subfactors and their connection to combinatorics, tensor categories, functional analysis, and mathematical physics. And today he will talk about planar algebra associated to cocommuting squares. Please.
Thank you so much for the introduction. And I want to thank the organizers for giving me an opportunity to present our work. So today I'm going to talk about planar algebras associated to cocommuting square. And this is based on a joint work with my advisor, Dietmar Bisch. So let me recall some basic definition. To one subfactor is a unital inclusion of two to-one factors, n and m. And the Jones index of a subfactor is a subfactor analog of the subgroup index. Roughly speaking, it measures how large m is relative to n. And because m is a to-one factor, we have a unique faithful normal trace. And using this trace, we can construct a GNS Hilbert space L2 of m and its subspace L2 of n. The projection E1 from L2 of m onto L2 of n is called the Jones projection. And the Jones projection implements the conditional expectation from large factor m onto subfactor n. Using the Jones projection E1 and the large factor m, we can generate a new von Neumann algebra denoted by M1. And this is a to-one factor if the index of m over m is finite. And this is denoted by this inclusion relation. A motivating example comes from a finite group action on a to-one factor. If we take a fixed point algebra, Mg inside a to-one factor M, then its basic construction is simply a cross product. By iterating the basic construction, we get a tower of to-one factors. This is called the Jones tower. And here, EI is the Jones projection for mi minus 2 inside mi minus 1. And EI lie in the relative commutant of n inside mi. And the Jones projections satisfy these three relations. There's a bimodule description for the relative commutants. Let rho be the nn bimodule L2 of m, and rho bar be its dual mn bimodule. Then the relative commutant can be identified with the endomorphism space of the tensor products of rho and rho bar. So the Jones projections lie in the endomorphism spaces. Kaufman introduced a nice diagrammatic expression for the Jones projection. And using these diagrams, we can verify the previous three relations. The rule is to stack the diagram on the top of the other whenever we multiply two elements. And if that creates a loop, we remove it and replace by a scalar delta. So in the case of E1 squared, we remove the loop in the middle and get a scalar delta. And the resulting diagram looks like this, which is the diagram for E1. And after removing the loop, we can freely homotope the diagram to obtain an identity. For example, in the case of E1, E2, and E1, the product has the diagram that looks like this. And we can straighten up the string in the middle to obtain the diagram on the right-hand side. And this is the diagram for a scalar multiple of E1. So far, we have composed the diagram vertically, but why not do it in the other directions as well? Von Jones showed that this is possible, and there's a well-defined way to tell the bimodule intertwiner that the resulting diagram represents. For instance, suppose we have these three diagrams on the left-hand side, and we can concatenate them by plugging into the tangle in the middle. So the first one goes to 1, second one goes to 2, and the last one goes to 3. And we insert the diagram in the way that the star symbols match. Then the resulting diagram looks like this, and this creates a loop in the middle. So we remove it and multiply by a scalar delta. And after homotopy, we get this diagram. In my talk, the linear span of the diagrams, together with the operation given by tangles, will be called a planar algebra. For audience from categorical background, this is just the two-category tensor generated by bimodules L2 of M and its dual. And this two-category is always strictly pivotal. Bisch and Jones went one step further and introduced a diagram for the Jones projection when an intermediate subfactor P is present. We went one more step further and considered a case with two intermediate subfactors, P and Q. N, P, Q, and M form a quadrilateral inclusion. And if we iterate the basic construction, we obtain a Jones tower that looks like this. Here, mi plus 1 is the basic construction of mi minus 1 inside mi with the Jones projection ei plus 1. Similarly, pi plus 1 is the basic construction of pi inside mi with the Jones projection pi plus 1. And qi plus 1 is the basic construction of qi inside mi with the Jones projection qi plus 1. Now I want to introduce the diagrammatic expressions for the Jones projection associated to quadrilaterals. First, we assign colors to the factors. Green to N, blue to P, red to Q, and yellow to M. Next, we express the bimodules with the vertical strings. And we color the regions on the left and the right by the corresponding factors. What you see here are the generating bimodules for the planar algebra. Now to take the tensor product of two bimodules, we just concatenate the strings horizontally. For example, the NM bimodule, L2 of M has two tensor factorizations. The tensor product of NP bimodule L2 of P with PM bimodule L2 of M, and NQ bimodule L2 of Q with QM bimodule L2 of M. So L2 of M has these two diagrammatic expressions. And the Jones projections, E, P, and Q has the diagram like this. These are the diagrams introduced by Bisch and Jones. These Jones projections outline the endomorphism space of the n bimodule L2 of M. However, we cannot compose these diagrams directly because the colors on the boundary don't match. To resolve this problem, we introduce a unitary isomorphism between two tensor products. And the unitarity can be represented as these two relations. Whenever you have a diagram, and if you want to take the adjoint, you just flip the diagram upside down. So in the first identity, on the left-hand side, we have the flip of U, so that is U star. And at the bottom, we have U. So this is U star U. And on the right-hand side, we have parallel strings. This is the identity. So this reads U star U is equal to the identity, which is the isometry condition. In the second identity, we have U at the top and U star at the bottom. And on the right-hand side, we have parallel strings. So this says U star is equal to identity, which is the co-isometry condition. So together, they form the unitary conditions. Now, for the diagrams with red on the boundary, we can conjugate it by U to get blue regions on the boundary. Then the Q1 has this new expression like this, and E1 looks like this. But thanks to this relation, we can push the bump over here to inside, and we can do the same for the bottom one. And we get the usual diagram for the Jones projection E1. So this way we get the diagrams for the Jones projections EI, PI, and QI. And just like before, when composing the diagrams create loops, we just replace with scalars. But now the scalars depend on the type of the colorings. So we have some relations for the planar algebras associated to quadrilateral inclusions. But identifying the complete structure of the planar algebra is a hard problem for several reasons. First of all, there are a few known examples of the quadrilaterals of 2-1 factors. Grossman and Jones studied the case of quadrilaterals whose elementary inclusions have trivial standard invariant. In categorical language, this means that the 4 sides have 2 categories that are Temperley-Lieb. And they show that all of such quadrilaterals are symmetric commuting squares with only 3 exceptions. The case of symmetric commuting squares have easy structures, so it is not that interesting. And second, there is no uniform structure for planar algebras associated to quadrilaterals. So to study the quadrilateral planar algebra, one has to impose natural and interesting conditions to begin with. And lastly, the dimension of the planar algebra is very large. On the table over here, I have the dimension data of different planar algebras. Here, n box space means the vector space of diagrams that has n strings connected to the top and n string connected to the bottom. And in the case of our interest, the 4-box space has dimension 1657. To understand the structure of the planar algebra, I listed thousands of elements in the 4-box space using MATLAB and found 1657 linearly independent ones without knowing what the dimension was. the planar algebras we studied satisfy these conditions. First, we have P2Q2 is equal to E2. This is called the cocommuting square condition. And in condition 3, we have that P1, Q1, and P1, and Q1, P1, and Q1 are linear combinations of two Jones projections. If the lambda was 0, then we get a condition called the commuting square condition. And together with the co-commuting square condition, we get a symmetric commuting square condition, which I introduced before. And to endow some degree of non-commutativity, we restrict lambda to have strictly positive value. But these two conditions do not completely determine the structure of the planar algebra, so we had to impose more conditions. Condition 1 gives the restriction to the index. Grossman and Izumi show that this condition is related to 3 supertransitivity of the inclusion n contained in P. Roughly speaking, supertransitivity is just a subfactor analog of the transitivity of the group action. Condition 4 and 5 says that we have two pairs of projections that commute with each other. By imposing this condition, we endow slight degree of commutativity to the planar algebra. These conditions may look complicated, but in fact, they are motivated by group action example. For instance, if we take the affine group of a finite field and take general linear group and its conjugate as a subgroup, then the fixed point algebras under these groups form a quadrilateral that satisfies all 5 conditions. More generally, we can construct a quadrilateral inclusion with arbitrary integer index by considering so-called graph planar algebra associated with this graph. And if we use the diagram, then we get an easy expressions for the previous analytic conditions. Under the index restriction, which was condition 1, and irreducibility, the remaining 4 conditions are equivalent to these 6 skein relations. Here, white regions are either blue or red. The only restriction is that you color the regions in an alternating pattern. And you may have noticed that there are some crossings that do not touch the yellow region, unlike before. And these crossings are defined by the formula at the top. Are there any questions so far?
Yeah, in fact, I have a question. So you consider a new family of subfactor planar algebra. It's like a Fuss-Catalan or like Temperley-Lieb, but it's another family which is new. Do you have is it infinite depth? Is it what kind of index do you have? Can you hear me?
Sorry, I could not hear the last part. Could you say that again, please? I heard up to the Fuss-Catalan part.
Yes, okay. Can you hear me better now?
Yeah.
Yeah, so you consider a new family of subfactor. So is it infinite depth or finite depth? What kind of index do you meet in this?
Oh, yeah. So we proved that these are all finite depth subfactor. And the index takes all integer values greater than or equal to 3.
Okay.
And non-integer values cannot be realized as the subfactor planar algebra. I'll present the detailed result at the end of the talk.
Okay. Okay, thank you.
Yeah, thanks for the questions. Are there any other questions?
No, no, it's okay.
Okay, good. Okay, so we have these 6 relations, and a natural question to ask is whether these relations form a complete presentation of the planar algebra. To prove this, there are 3 things to check. First, any closed diagram has to be reduced to a scalar. This can be viewed as a 2-dimensional analog of the word problem in group theory. And we require this condition because the closed diagrams are a trace of an operator, which has to have scalar value. And in categorical language, we need it because the simplicity of the factor is translated to the simplicity of the one-morphism, unit one-morphisms. And only few evaluation algorithms are known, such as jellyfish algorithm, exchange relations, and Yang-Baxter relation. But none of them were applicable to our case, so we introduced a new algorithm. And I want to thank Professor Liu Junhwi for pointing out that Yang-Baxter relation could possibly considered in this setting. And secondly, for each assignment of the colors on the boundary, we need that the corresponding vector space to have finite dimension. This corresponds to the finite dimensionality of the morphism space in the 2 category. And lastly, for all elements x, we need that x star x is greater, it is positive, and x star x is equal to 0 if and only if x is equal to 0. And we want this condition because we want our planar algebra to be an operator algebra. I would like to explain the proof of these 3 conditions. And I'll start with the evaluation algorithm. So the idea is to split the yellow regions into smaller pieces as much as possible. When all yellow regions become bygones, there's an easy way to remove them. And if there is no yellow region in the diagram, we can easily reduce to a scalar. And if we cannot split the yellow regions, then we can show that the diagram is equal to 0. So this is how the algorithm works. Without loss of generality, we may assume that our diagram is connected by choosing the innermost component. The first thing we do is to remove the loops, monogons, bigons, and edges of this type. The only monogon that can appear has this form, and using our relations, we can prove a relation that is reminiscent of Reidemeister type 1 move, so we can remove a monogon. And here, I listed all possible bigons, and we can show the relations that remove these bigons. And lastly, this is just one of the relations I introduced before, and because of that, we can just get rid of this edge. Next thing we do is to consider the substructure of the diagram that can be simplified. And to rigorously define the substructure, we assign the signs and orientation on the strings. The signs will be expressed as colors, blue for positive and red for negative, and orientations are expressed as the arrows. And there's a substructure called a vanisher, and this is simply a region enclosed by a cycle with certain sign pattern. And if we have a vanisher in the boundary, then the entire diagram becomes 0. So in this case, there's nothing to do. Now suppose there is no vanisher. Then we consider another substructure called a bubble. And if you have a bubble, then sometimes you can pop the bubble and split the neighboring yellow regions into 2 parts. This way we can split the yellow region into smaller pieces. And after doing that, we go back to step 1. And if we could not split the yellow region, we consider another substructure. And this is called the garden because later we will use the flower relation on the right to enlarge the garden. The enlarging process looks like this. At the bottom, we have some part of garden. And next to a garden, we have a yellow region. We apply the flower relation to the yellow region. And if we apply one of the relation I introduced before, then we get a larger garden. After doing that, we go back to 1. And we can continue this until we can no longer enlarge the garden. And when this happens, we are guaranteed to have a vanisher. So we have 0. So this is how the algorithm works. And as a byproduct of the proof, we obtain the sphericality of the planar algebra. This means that we can homotope the closed diagrams as if they are embedded in the 2-sphere. Next, I'll introduce the proof for the finite dimensionality. But before we move on, are there any questions? Okay.
It's okay. Okay.
Oh, okay. Yeah, so the next thing I have to show is that for each assignment of the colors on the boundary, the corresponding vector space is finite dimensional. To compute the dimension, we introduce a set partition valued invariant for diagrams. For now, let me only consider the diagrams with green, blue, green, blue, green, blue coloring patterns on the boundary. First, we will construct a graph from this diagram and extract the set partition. The first thing we do is to remove red and blue colorings. And after that, we remove some crossings. And we place square vertices to yellow regions, white circular vertices to white regions, and black circular vertices to the white intervals. And we label the black vertices from 1 to n clockwise. Then we connect the vertices with edges, and the last step is the trickiest part. We separate the square vertex into 2 parts. So whenever you see square vertex, you should regard it as an overlap of 2 distinct vertices instead of a single one. Here, the edges are colored the same if and only if they are from the same component. And from this, we can extract the partition data from the connectivity. For example, 1 is connected to 3, 4, and 9. So in the set partition invariant, we have a block that consists of 1, 3, 4, and 9. Similarly, we have a block that consists of 2 and 11, 5, 6, 7, and 8, 8 and 10, and 12. And we show that the diagrams are equivalent if they have the same partition invariant. And using this result, we show that our planar algebra is isomorphic to partition algebras. Partition algebras are linear span of the partition that can be expressed by these diagrams. And the multiplication of the partition algebra is defined by stacking a diagram on the top of the other. And if this creates an isolated component, we replace by a scalar t. In our case, the t represents the index of p over n, which was alpha squared. A factor of t squared. On the left-hand side, we have the generators of the partition algebra, and the isomorphism from the partition algebra to our planar algebra looks like this. And to show the isomorphism, we have to show surjectivity and injectivity. For the surjectivity, we show that for a partition D, the image under the previous map phi is the diagram whose partition invariant is D, plus negligible error terms. For injectivity, we divide into two cases. The case where alpha squared is an integer and where it is not. For the non-integer case, we have a basis of the partition algebra whose dual bases have a planar algebraic description. And by applying phi to this sorry, I guess the connection was not stable. Could anyone tell me where we have left?
It was on this slide.
Okay. Did we have good connection when I was talking about injectivity for non-integer case?
It was to know that negligible error terms. Negligible error terms. You are talking about negligible error terms.
Sorry, I cannot hear you well.
You were talking about some negligible error terms.
Oh, this part. Yeah, so because errors are negligible, we have the surjectivity. And to prove the injectivity, we divide into two cases, where alpha squared is an integer, that was the index of p over n, and where it is not. For the non-integer case, we have a basis of partition algebra whose dual basis looks like this. And this dual basis have a completely pictorial expression. And if we apply the map phi to these dual bases, we get a linearly independent functionals on the planar algebra. So this proves the injectivity for the non-integer case. And when alpha squared is an integer, an extra care needs to be taken because the formula for the linear functional is 0 over 0. But these can be regarded as the removable discontinuity. So the same result can be extended from the non-integer case. Okay, before I move on, is there any question?
Okay. We can continue.
Okay. Yeah, so using this isomorphism, we could easily show that the dimension of the planar algebra with green, blue coloring pattern on the boundary is the Bell number, which counts the number of the set partition, which consists of n elements. But what we are more interested is the dimension of the vector space with green, blue, yellow, blue, green pattern on the boundary, because those corresponds to the relative commutant of n in the basic constructions mi. And to compute the dimension, we consider the embedding of this vector space into the vector space with only blue and green coloring on the boundary. And if we consider the partition graph, we can show that the dimension is equal to the generalized Bell number, which is the number of set partition of 1 to 2n, such that each block does not contain both 2i minus 1 and 2i for all I. The generalized Bell number was first introduced by Blasiak, Penson, and Solomon as the solution to the boson normal ordering problem. And Kodara, D'Antona, and Hill introduced the combinatorial interpretation. Yeah, and as a corollary, we could show that our planar algebra comes from subfactor if and only if the index of p over n is an integer greater than or equal to 3. When this is not the case, we can always find a projection whose trace is negative. So this does not come from a subfactor. And in the case of alpha squared is integer greater than or equal to 3, we had the previous example coming from the graph planar algebra. So we have the equivalent conditions. An interesting thing to notice that when we show the isomorphism of the partition algebra and the planar algebra with green, blue coloring at the boundary, we prove the property of the case where alpha squared is integer from the property of the case where alpha squared is not integer. This turns out to be, we proved the property of the subfactor planar algebra from non-subfactor planar algebra. And lastly, we have that the tensor category generated by NN bimodule L2 of M is the representation category of the symmetry group Sn, where N is the alpha squared, and that was the parameter for the index of P over M. To prove this, we use the fact that the partition algebra is the endomorphism space of the permutation representation of the symmetry group. Tensor powers of the permutation representation. And the permutation representation generates the entire representation category. So that's why we get rep Sn. And another thing to note is that in the case of non-integer parameter, we get the Ling category. So this completely resolves the problem under the condition motivated by group examples. Thank you very much. Sorry, I finished too early.
Could you characterize the dual tensor category?
The dual tensor category?
Yeah.
So the you mean the bimodule category over L2 of M?
Mm-hmm.
Yeah, that is the representation category of Sn minus 2.
Mm-hmm. Okay. So can you re-explain quickly the model, the initial motivation you said? So that there is this family, Fuss-Catalan by Bisch and Jones, and you started from a model. You said it's a cocommuting square. So if you have a subfactor with two intermediate, you always have you don't always have such a cocommuting square. It's something specific.
All right.
It's but every subfactor with such a cocommuting square contain your subfactor planar algebra as a subplanar algebra. As for Fuss-Catalan, it's always contained inside. So it's like a universal model for this kind of.
Yeah, let me go back to the example. Yeah, so the conditions I consider was these 5 conditions. And the easiest examples of quadrilateral inclusion was the symmetry commuting square, which is both commuting and co-commuting. And we wanted to go one more step further. So we considered a case of co-commuting square that is not a commuting square. And that can be also separated into like infinitely many cases. And we consider the most simple case where the product of Jones projections P1, Q1, and P1 and Q1, P1, Q1 are linear combinations of 2 Jones projections. In general, they can be linear combinations of multiple projections, but this was the simplest case we can think of. But the problem was these two relations do not completely determine the structure of the planar algebra, so we looked at some example coming from group actions. And we found an infinite class of groups that gives you a cocommuting square satisfying this third condition. So that's one of the reasons why we consider the cocommuting square. And from these example, we extracted the other three conditions, which are condition 1, 4, and 5. Still, there are some other cocommuting squares that do not satisfy, for instance, 1, and that one has different structure than the structure of our planar algebra. Sorry, did I answer your question?
Yeah, more or less. So my question is, so you provided an example coming from finite group theory, I guess, in the next slide. So do you expect examples do not coming from finite group theory, or they are all of this one? Because at the end you said you recover rep of Sn. So it seems like it's inside the finite group theory. No?
Yeah, so what I suspect is the condition 5 is a strong restriction that we only get an example coming from groups. But condition 1 to 4 is also satisfied for the quadrilaterals of, let's say, the Hagorev subfactor and AH plus 1, and AH plus 1 and AH plus 2. So these are the next example I wish to study. And these do not come from the group.
Okay. Any question online?
I want to ask about, so at the end you have this equivalence with rep Sn. Can you hear me?
Did you say I got the equivalence with rep Sn?
Yeah.
Okay.
So there's this construction in which I construct like a two category in which I put all the rep Sns together, right, by varying n. So I have a two category whose objects are natural numbers, and then on top of it, the homomorphism categories are rep Sn, essentially.
Sorry to interrupt you, but I cannot hear you well.
Can you hear me now?
Yes.
Okay, so my question is in two parts. One of them is there a way to, so there's this construction of a two category in which the objects are natural numbers, and the morphism categories are rep Sn on top of each natural number. And the monoidal structure is like just adding n, basically. So my question is there something analogous on the subfactor side, right? If I think of the bicategory formed by, the monoidal bicategory formed by a whole bunch of like these one-element algebras. And the second question is, because rep Sn is symmetric, is there a way to get a braided back instead of a symmetric tensor category?
For the second question, I don't know the answer. And for the first question, yeah, so you said you were assigning rep Sn to each object n.
Yeah.
Do you mean that you have a two category whose endomorphism of the object is rep Sn?
Yep.
Yes, I guess we can construct a subfactor like that. So what we can do is to consider S infinity. And since S infinity is countable and hyperfinite to one factor admits the group action of any countable groups, we can consider the group action of S infinity on the hyperfinite to one factor. Then what we can do is to consider the fixed point algebra under rep Sn. Then the bimodules associated to those subfactors, sorry, the fixed point algebra will become the object N, and the endomorphism category generated by the fixed point algebra, the original hyperfinite to one factor over the fixed point algebra will become rep Sn.
Okay. Okay, I see. Okay. Okay. But well, in regards to the second question I asked, it's because there's this thing called Sorgo bimodules, in which I can actually, on the side in which I have this two category with objects given by natural numbers, I can construct like home categories which are braided things, like representations of some Hecke algebra, for instance. So like these type of like categorified Hecke algebra is they're called Sorgo bimodules, basically. It's called SSBIM, sorry. So I'm just wondering, like, if we're able to kind of generalize this subfactor story to also include these braided like these braided things to the Sorgo bimodule story, then I think you can say something about Hovnau homology. So
Sorry, did you say Kovanov homology?
yes.
Oh, yes. Sorry, I don't know about Kovanov homology, so I don't have an answer to your question, but it is very nice to learn this fact. What I suspect is subfactors may not be a good tool for studying braided category because usually we don't have the braiding.
Or maybe there's a generalization. Because I want to think about quantum groups, for instance.
Oh, yeah.
Or maybe subfactors is like the thing you get from quantum groups, but you already modded out by scheme relations and stuff, so you don't have any crossing. So maybe there's a generalization which I can recover, the Hecke algebra before I do with the potion down to the Temperley-Lieb, but maybe something analogous can be done. I don't know.
Yeah, sorry, I don't know the answer to your question.
Okay, I'm just randomly asking. Thank you.
Yeah, actually, could I email you after the talk? I want to learn more about this construction.
Sure thing. Yeah.
Yeah.
Like,
can I get?
You're referring to the Sorgo bimodules, you mean, or?
Yeah.
Okay. Yeah, of course.
You want to write your email?
Yeah, like you was asking, or I can email you.
Oh yeah, that would be great. Thank you.
Yeah. Okay. Yeah, no problem. Thank you.
So I have another question. You talk about a Deligne category. So your construction recover the Deligne category, but at the end, it's not positive. So what you are saying is that Deligne category are not unitary or something like that.
Sorry.
You are saying that
I want to make sure
The link category fail the positivity. You talk about the link category when n is not an integer.
Yeah. And you said the link category is not positive?
So this is what you said, no? It's failed to be positive. That's why you can.
Right, you're right. So the link category is never positive, but in the case of integer parameter, we can consider the semi-simplification. Then we get a C star category, and that becomes the planar algebra of a subfactor. And in the non-integer case, the link categories are already semi-simple, but it does not have a C star structure, so it cannot be a subfactor planar algebra.
Okay, but your construction can still make the category, even if it is not a C star category.
Oh yeah, so to construct the link category, you just yeah, let me go back to the slide where I had the relations. Yeah, so using these 6 relations, you can construct the link category. And if you take the semi-simplification using, oh no, not this. This last analytic condition, then we get representation category of Sn. And if we don't do that, we just get the link category.
Okay. Okay.
Oh yeah, and yeah, I remember that you asked about the depth of the subfactor, and since because the category is rep Sn, the depth is finite.
Sure. Okay. Any other question online, maybe? No? Any comment? No. Okay, so let's thank you again.
Thank you very much for having me.